So we're learning about p-value and the sample test statistic. We had left-tailed, right-tailed, all that sort of stuff. And sometimes calculating the test statistic can be very confusing. You got to pay attention. Probably the thing you guys ignore the most is the alternate hypothesis, because it's the alternate hypothesis that tells you which way you're going to go, right? So we have here, this is from the reflection. So if you want to take some notes, you can. This looks a lot like what we did before. We have a new fertilizer has been developed by the graduate students in the plant sciences department at your school to increase tomato yield. All right. And in fact, you know what I'm going to do? Who would like to be able to open their, Ashley, I'm going to take a pause. Would you like to be able to put the right answers on this on your reflection while I go through it? Yes. All right. So I'm going to stop for a second. I'm going to change it to WebAssign because I don't have WebAssign on there. All right. So you can follow along. And then let me do one other thing. Let me make sure you can open it because I'm pretty sure it's closed. So give me 1 second. So we know, we've talked about this. The level of significance is 0.05 because it's the same as the alpha. So make sure you click 0.05 on your reflection. Huh? All right. While you click on that, then the next question, here, let me go ahead and do this for shapes. Level of significance on this case is 0.05. Shape fill, none. Shape fill, none. There we go, no fill. Okay, so that is the correct answer for the first reflection part. Let's go to the next one. State the null and the alternate hypotheses. So when you're doing that, stating the null and the alternate hypotheses, the important thing is to say, what are they worried about, right? So what are they worried about? Plants what? Okay, so we're like greater than? Yeah, we're trying to increase. Very good. So increase is what we're interested in here. We're increase the tomato yield. So that means we're worried about greater than. And we know it's never the it's never this not equals to or greater than here. So the correct answer will be, there we go. Correct answer should be D in my case. The values are equal, but we're wondering if the difference is greater than 0. So this kind of sample right here is a little different. You remember how we do we haven't done averages minus averages yet. So now we have two sets of data, right? A before and an after. And you can see how each one is paired. By the way, Bud's out, phone's out of my sight and yours, please. Thank you. So we're looking at the actual differences. So the increase for plant 1 is 2. See how it's matched on plant 1. Both that value 3 and the value 5 relate to plant 1. Do you know why we subtract it and then look at the differences? Any ideas? Bud's out. Table 8, Bud's out. Thank you. Both sides. All right. So the reason we look at the differences is if I were to take the averages here and then the averages there, you might lose the increases. You won't see how big an increase is. If you can actually measure the increase for each plant, you have a much better idea of the data. So this is called a paired t-test, all right? Next question, what sampling distribution will you use? So again, this is something you need to remember. Are we dealing with proportions or are we dealing with means? With means or averages, guys? Are we dealing with proportions or with means? We are we? We're dealing with means. And with means, unless you know sigma, it's very rare, use the student's t. We always use the student's t for means. And I used to teach you how to do it when we use the normal for means, but that's very unusual. AP occasionally has to deal with that, but you guys don't. So we are dealing with means, so we use the student's t distribution. Now, did these two say the same thing? Oh, one says a uniform distribution, one says a normal distribution. Have we ever used a uniform distribution? No. So I'm going to say the answer is A on this. It's the student's T, and we assume that D has an approximately normal distribution. Got it? Okay. Then we're going to go to what is the value of the sample test statistic. So we're going to pull the Stapplet out again. All right. Now, when we pull out the Stapplet, here's the deal. On your test, you're going to have to tell which Stapplet you need. For this one, we're doing means. Is it, and we just have one set of differences, right? We're just interested in this data. Okay. So the question is then, do we want the normal, the one categorical variable or the one quantitative variable? Which one do we want? Which one do we want? It is quantitative because we're looking at the actual differences. All right. We want one quantitative variable. All right. So one quantitative variable right here. And then what I'm going to do is you guys can see on the WebAssign, which you have on your computer, you see the data, right? So I'm going to just type it in here. 2, 4, -1, -2, -1, 3, 4, 1, right? And the variable mean is the increase. The increase is the difference with the before and after. Okay, so there's our dot plot. And usually you're going to check to make sure there are no crazy outliers in there. Then we come to perform inference. And we are we're doing a hypothesis test. How do I know we're doing a hypothesis test? Well, because if you look at that second question, part B, we were stating hypothesis. So it's a test. And it's a one sample t-test for mu. And I'm wondering if the difference is greater than 0. Usually for differences, this number is almost always 0. All right. So that number is almost always 0. And then you perform inference and voila, there's the test statistic and the p-value. It should match one of the answers on your WebAssign. Okay. Quantitative. Any questions on how I did that? Use one sample t-test, I'm sorry. And mu is greater than 0 for alternate. All right, so I'm kind of writing you some notes here. So if I come back here, it's almost always greater than 0 for the hypothesized value. All right. So the correct answer on here, the test statistics is 1.4884. And then when we go to the p-value, right? Well, we have it right here. What's the p-value? 0.0901, right? Let me hang that up. All right. So it's 0.0901. So in that case, all we have to do is go ahead and click off 0.0901. Does this look a little bit familiar from what we've done before? It should. It should be pretty much the same thing we did before, except for one thing. We got to subtract the numbers and then use the differences, and that's it. Right? So in a way, this was good practice for your test next class, because the difference is you wouldn't have these two values, right? So let me go ahead and turn back on the Blocksy with our Desmos. Let me start assessment. Desmos. And we're going to go ahead and look at this in a more real life situation. It's not perfect, by the way. When we get real life situations, the data is rarely perfect. Okay. Very rare that it's perfect. So let's go ahead and confirm. All right. So let's go to the Desmos. Start the activity. So you guys can share what you think. I'll admit, honestly, when this whole global warming thing first started, I was more of a skeptic. Usually I tend to stick with the assumption that things are the same. until someone gives me data that it's different. You know what I mean? Kind of like the null hypothesis. I like evidence. So you can tell me now, how concerned are you about global warming? You're allowed to be concerned. You're allowed to not be concerned. Let's see how you guys are doing. You're all over the map. Some of you not very concerned at all. Some of you very concerned. And would it be a different answer for me than for you guys? Why? I'm ancient. I'm 55, going on 56, right? So 40 years from now, I probably won't be alive, but you probably will, right? So who knows? Honestly, for me, I'm like, yeah, I'm actually seeing, like, we've never had a tornado through our property until this year. Yeah, I mean, through our neighborhood. You know, when has a tornado ever hit Round Rock, actually? They haven't. You don't have tornadoes in Round Rock. You just don't. And then we had a bunch. So who knows? But that said, yeah, I'm a little more concerned about it now. We're going to actually look at some data. Come on, move. And scientists say climate change is real. Again, I'm still waiting for the data. About 97% of climate scientists with PhDs say it's real. And they also say it's caused by humans. Now that one, who knows? I don't know. All right. Because I'd have to look at what data they have. And I honestly haven't studied this so much. Okay. Now, there has been climate change skepticism. Have you guys heard of Michael Crichton? Who's heard of Michael Crichton? I'm pretty sure he's the one that wrote Jurassic Park, right? You guys have heard of Jurassic Park. That's a good one. Yeah. So he tends to look at things in science and then try to take them out and make a really interesting story about it. So here, it's a bestseller, and it remains one of the most cited works by climate change skeptics. Even though it is framed as fiction, he did not give him credit. He did not say it was real. All right. Has many graphs of real data, footnotes to scientific articles, and a 20-page bibliography. Okay. Wow. And it was made required reading for the Senate Environment and Public Works Committee. Okay. And he actually did testify in front of them. So, question is, who do you trust? Do you trust 97% of climate scientists or 3% of climate scientists and Michael Crichton? You're allowed to trust whichever one you want. By the way, there is a culture in scientists. For example, string theory. How many of you heard of string theory in physics? Anybody? Yeah. There's question. People seem to think it's true, even though we don't really have good math to say it is. So I'm not going to say that scientists don't get off on their own thing. They do too. So it actually happens in the physics community. But I think most of you, a couple of you say you trust these guys more, but most of you trust these guys more. Okay. I think we've seen, by the way, a change before when with the COVID. A lot of us were a lot more concerned, rightly so, and it really mattered what the CDC was saying, I would say. Now we're kind of at the point, most of you don't have your mask on anymore. Some of you do, and that's fine. And if you ever need me to wear mine around you, I'll do that. I'm a little more comfortable with the whole no mask situation. So if you were to go to the CDC, what kind of guidelines would the CDC give you? What do you think they're supposed to do? Right, because why? What's their job? They're trying not to have anybody die, right? And they're trying to minimize disease. And it's good advice. So those of you still wearing your mask, good for you. All right. I can't do it anymore. Well, I can, but all right. So does the data, so what we're going to look here is we're going to see, does the data and state of fear disprove climate change? Because he does share data. So let's look at the data he pulls up. In the book, he goes to, it's the record from the weather station at Punta Arenas near here. It's the closest city to Antarctica in the world. He tapped the chart and laughed. There's your global warming. So what's his point looking at this graph? That is a set of data. If you just use that graph to make your judgment, what would you say? Wouldn't you say the temperature's going down, not up? Yeah. So just based on that graph, you would say, oh, there's no global warming good. That's a good counterexample to the global warming argument. It is, right? There's a reason people don't disagree on that. People disagree on things like this. Okay. So what we're going to do, let's see, was there anything else? What does the graph appear to show? It looks like the Earth's cooling down, not warming up. So temperatures, find the difference in temperature and Punta Arenas. So you have 1901 to 1950, it's 0.828 in Celsius, by the way. And the reason it's 6.828, so it's just a little above freezing. And then 1951 to 2000, 6.752. So the temperatures actually tended to do what? Go up or go down? Go down, right? So if I actually went ahead and subtracted this, 6.828 minus, I'm going to actually do after minus before. Okay. After minus before gives you the direction of change, 6.828. And the answer is negative 0.07. So it looks like it was decreasing, right? So it looks like it's decreasing. Now, temperatures are averages of the meteorological annual mean temperatures from those years in Celsius. Data is collected from the adjusted clean data set from NASA, which they describe as adjusted data after removal of some outliers and duplicate records. He appears to use the unadjusted and unclean data in state of fear, but in this case, it's not a big deal because the unadjusted and the adjusted seem to be matching pretty well. All right. So that is a data point. That is a piece of evidence that doesn't support global warming. All right. What about the rest of the world? So what we do is we're going to randomly sample 32 pairs of latitudes and longitudes and find the nearest temperature station for each set of coordinates and get 2 measurements per station. Does this sound kind of like our tomato data? We're going to do, so let's go ahead and get those. And what we have here, you can highlight in orange. I'm not going to make you do it all, but where the temperature decreased. So this one went up. This one's the same. Let me change to orange. So they're looking at all of these. This one went up. That one went up. I'm looking 26.404. This one went down. And this one actually went down a little, believe it or not. Might be hard to tell. And I'm looking here, 0.43, went up, went up. This one went down a teensy bit. Went up, went up, went up. So most of these have gone up. Have they gone up by huge amounts necessarily? No, the changes are very little, right? So let's see, does that one go down? No. Yes, that one went down, actually. That one got colder. But most of these are, let's see if he has, which ones are highlighted. So if you look at them, most of these did have the temperature increase. Only a few of them had them decrease. All right. So for how many stations did the temperature decrease? It was a couple. I'm going to say a couple. Should I go back and count them? Let me go see. Mrs. Overman. Okay. Up, 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 up. So I'm counting 4. Is that what you guys got?
I got 5.
Oh, which one also decreased? I missed one. Oh, right here?
Above the third one.
Above the third one. This.
Oh, the third one.
My third mark. Okay. Oh, yeah, this one went down too. Thank you. Thank you. So we had 5 stations decreased, right? I'll just put 5. It wants a number here, I can tell. All right. So the data has a blank structure. Let me go ahead and go there. 1 second. So we have what's called a matched pairs structure here. And each individual one has 2 measurements. We find differences within each individual, right? So we have a difference for each individual, right? The matched pairs is useful because we are controlling for variation. So the thing is, if I were to take just the averages of all these places, what would happen is you wouldn't really see the differences because you've got degrees. If you look at those temperatures, you got stuff at freezing practically, and then you have very warm. So if you did those averages, the standard deviation is so huge that you can't tell if there are differences. So if I had done just the average temperature here and the average temperature there and try to test that, I would not be able to see what was going on. Okay. So, what should we have on this? Not too bad. All right. So, for how many stations did the temperature decrease? Okay, so let's go to the next. So, mark on the number line where no difference in temperature would be in green. So, let me go ahead and get green. There's green. No difference in temperature is right here, right? So, if we look at that, what do you notice? Did we have more places go up in temperature or more places go down in temperature? Up. We had more places go up in temperature. All right. By the way, you guys do know there's also cyclical, non-human caused temperature changes, yes? I mean, think about it. We had the Ice Age. Were we really around causing problems back then? No. So you can have, if you really want to change the temperature, you know what's the best way to change temperature? We can't even compete. Have a nice couple of volcanoes go off. Or have a comet hit the planet. Let's not do that, though. That's not good. All right. So there is a cyclical nature to temperature. What we're really trying to figure out here is what we're seeing is really unusual. So in this case, we're just looking at the estimate for the changes here. So is Punta Arenas representative of climates around the world? What would you say? I would say no. Right? Looks like your median of these is closer to this. Well, how would we get a more representative measure, the typical change in temperature across the world? I probably actually would prefer the median. All right. Let's see. Typical change in temperature around the world. Let me make sure I'm looking. So we could find the average. Why wouldn't we do the median? Because we're not as good at doing stats on medians. Medians are a little trickier. But we can definitely find the mean change in temperature. And actually, this doesn't look very skewed. It looks somewhat like a mounded data with no major outliers. So we're probably fine using this data. Okay. So stations showed warming on average. So let's test. Is the average temperature change significantly? Do we want to say significantly different, significantly higher? What do you think we want to do on that one? So we'd probably say positive here. Let me put test. Right? Greater. I'm going to put greater. Right? So, and actually, I'm going to say greater than 0, which is basically positive, right? Greater than 0. Okay. So we're going to test, and I'll go ahead. So mu d is that the difference in the true difference is 0, and our alternate is we're worried that it's greater than 0. All right. Conditions, we did take a random sample. Our sample is less than 10%. How many did we take? 20 some, 25, I think. Where was our data? 32. So 32 is less than, we're almost done, 32 is less than 10% of all weather measurements in the world, or we'll say weather stations. Really, because it's kind of hard to say. So we'll say you have weather stations. Is it normal? The data doesn't show any strong skew or outliers. So this is fine. All right. So we're doing a one sample t-test for D. There's an alternative calculator link. Good for them. Did I do GeoGebra? I did do GeoGebra. I'm going to go ahead and do Statlet. So let me go ahead and use Statlet for it. So what we're going to do is www.statlet. Did they give us stats? Please say they gave us stats. No, I got to put the data in. Really? Hold on. That was a lot of stations. I don't want to put in all that data. Okay, so here we go. I'm going to tell you that X bar, which is our average, is 0.35. S of X equals 0.296, and N is 32. Right? And we're going to basically do a confidence, well, we don't have to do a confidence level. We're going to go ahead and go to the Statlet and put this in. We're dealing with one quantitative variable again. I'm going to put mean and standard deviation because I don't want to put all that data in. And I have 0.35 was the mean temperature. Standard deviation was 0.296 for the sample, and we had 32. All right. Temperature differences. Begin analysis. And we're doing a t-test because we have hypothesis. We're worried that it's greater than 0. And in this case, you can see there's our test statistic, 6.68. All right. And there's our p-value. So we're saying that if there really is no difference, this does not match our data. Our data says, hey, there really is a difference. Now, that said, if it's like a 0.1 degree difference, you don't know. This creates its own boundaries. But if we wanted to know what it really was changing by, we could do a t interval. And it looks like it's changing by about anywhere between 0.24 and 0.45 degrees Celsius. All right, those two data sets. So we're talking about 1 degree Fahrenheit. What does that mean? Not sure. They're still working. It's a very hard problem, so they're still working on it. All right, where am I? Here I am. So the p-value, let me pull it over here so I can copy it. So the p-value is let me go back to the t-test. So our test statistic is 6.688. And once you start getting high, like 4 or 5 for your test statistic, you know that's an issue. We had 32 weather stations -1, so we get 31 as our degrees of freedom. Our p-value is less than 0.001. So our conclusion is we're going to reject the null. Reject H naught because our p-value, which is less than 0.001, is less than an alpha of 0.05, right? We have convincing evidence that the true difference in temperatures that temperatures have the true difference of temperature are positive, i.e. temps have increased, right? All right. Okay. So submit that. Almost done. So we reject the null hypothesis that the true average in global temperatures has changed. Since our p-value is less than 0.05, there is sufficient evidence to conclude that our temperatures are greater. All right. So that's how we construct it. And then visual, he kind of was cherry picking his data, because if you look, this is kind of like a temperature difference in Fahrenheit. So if you pick your data there, maybe you go over here somewhere, you could find counterexamples, right? So last but not least, you guys have been awesome. So when it's correct, the title will change. So do you think the data collected, oh, this is great practice for your test, all right? 2 proportions is when we have 2 samples, and 1 proportion is when we have 1 sample. So I'll walk you through it. We got a 1 sample t-test. Oh, 2 1 sample t-tests. Yeah. You want to test more than 20% of your students at your school have made a TikTok. That's a 1 proportion z-test. According to a recent study, the typical teenager has 183 contacts stored in their phone. So that's an average. So we do that one. Do Duracell batteries last longer than ever ready? So that's an average. That's called a 2 sample t-test. We'll actually do that next class. Which brand of razor gives a close shave? They have razor A and razor B. So that would be a matched pairs t-test right there. There we go. And then finally, who is more likely to post Instagram stories daily, middle schoolers or high schoolers? And why didn't my title change? Oh, I'm missing a. Why do I have more than 1 sample t-test? That's so weird. Let's see. I think there's a typo. I need to go edit this. What happened here? All right. So I will agree. That is the answer, and I need to go figure out why it's not. Oh, do teenagers. Here we go. I get more than the recommended steps. That's why I don't have the right answer. And I'm going to guess that these are. I want to make my title change. There we go. All correct. All right. Oops. Go back. Okay. And we're done. Let me